In the previous lecture, I have discussed the image transform, the basics of image transform. I have discussed the basic backgrounds of the image transform. In the previous lecture, the basic representation of the image transform and the basis function and the different types of the transforms you have studied in the next lecture. In the previous lecture, I have discussed the Fourier transform. What are the basic backgrounds of the Fourier transform working? In the basic background of Fourier transform, this is the formula of the Fourier transform, and then how to represent the two-dimensional Fourier transform representation of a 2D signal, and this is the representation of a two-dimensional discrete Fourier transform. Here this is a one-dimensional Fourier transform representations. This is a quick revision of the two-dimensional Fourier transform representation and what are the application of the Fourier transform. Here this is the basic representation of the Fourier transform in the case of image. Image is a two-dimensional signal. In the previous lecture, I have discussed the magnitude and the phase characteristics or phase response of a given image signal and what are the importance of the phase characteristics in the image domain. Here, for example, you have taken the two images, image A, image B. Here you have read the image as classified as image A and taking the Fourier transform of this image and then taking the magnitude and phase characteristics of this image, and then this is the phase characteristic means you have find out the phase angle also. This is a basic principle of a phase response calculation. Magnitude you have also studied in the signal system class. Just what is the importance of the phase calculation in the image. Then you are taking the inverse Fourier transform and get back to the reconstructed image A1. This is the A image. You have new nomenclature as A1. Then same approach in the second image. This is treated as the image B. Here the Fourier transform of this image, you have find out the magnitude and the phase, and this phase goes back to this image A and taking the inverse Fourier transform of reconstructed image. Then this is the pictorial representation of importance of phase in this image. The original image is taken as image A. This is a cameraman image, and second image, original image, is a Lena image. What is the role of phase response phase calculations in this image processing domain? First, taking the image 1, this is the cameraman, and cameraman image after phase reversal. In the block diagram, you have taken the phase angle calculation and fused the two images, and here this after the phase reversal of a cameraman image, here the phase characteristic, feature of the phase of a Lena is more dominant. Here the phase of a cameraman is some written. Then Then here this cameraman image has the phase angle, but the dominant feature is obtained in the cameraman. यहाँ पे आफ्टर फेज रिवर्सल, यहाँ पे आपका इसके जो फेज कैरेक्टरिस्टिक्स हैं, इसमें जो आफ्टर द फेज रिवर्सल उसमें कुछ कंपोनेंट लेना के भी हैं, तो लेना इमेज के जो फेज फीचर्स हैं वो डोमिनेंट हैं। तो आफ्टर द रिवर्सल दोनों इमेज के हमने फीचर कंबाइन किया है, तो यहाँ पे हम लेना इमेज के जो फेज कैरेक्टरिस्टिक ज्यादा है, तो वो आपका फीचर इसमें ज्यादा दिख रहे हैं, ठीक है। और इसमें आपके इस वाले में आपके कैमरामैन के, तो ये सब है कि आपको कहां पे यूज करना है, फेज इंफॉर्मेशन से क्या इंफॉर्मेशन हमें रिट्रीव करना है, और मैग्नीट्यूड कैलकुलेशन से हमें क्या फीचर को कैलकुलेट करना है। तो दोनों का इंपॉर्टेंस है। दिस इज द ब्यूटी ऑफ द इमेज ट्रांसफॉर्म, हाउ टू कैलकुलेट द इमेज ट्रांसफॉर्म फॉर द डिफरेंट एप्लीकेशन। Then the application of Fourier transform in image processing. In the previous lecture, I have discussed the basic application of image filtering. The basic image filtering we have used in this domain. Here simply you have taken Fm, this is the input image, and Hmn is the impulse response of the filter, and Gmn is the after the filtering operation, the output is denoted by Gmn. Then this mathematical representation of this filtering operation is written as Gmn is equal to Fn convolution Hmn, ठीक है। तो this is the basic representation of Fourier transform in the image processing application. Here you are taking the input image after taking the Fourier transform, discrete Fourier transform, and then get back to the Fourier transform spectrum of this image and goes to the filter function HKL, and then this goes to output of this filter function goes to the inverse discrete Fourier transform to get back the original image. Here you have taken the Fourier transform of a given image to find out the spectrum of this image, and reverse discrete Fourier transform to find out the original image. Means you have taking the Fourier transform of the given image to find out the spectrum of a given image, to analyze the spectrum frequency of this image. This is all about this is the beauty of the Fourier transform, discrete Fourier transform in the image processing. Means the use of the Fourier transform is to compute the mathematical computation is easy. For example, the time domain, it is a convolution. In the frequency domain, this is the multiplication. This is the basic beauty of this domain. Then I have discussed in the previous lecture the Wavelet transform. You have also discussed, this is the non-sinusoidal Wavelet transform. Non-sinusoidal transform, because this is the basis function is a non-sinusoidal function. And then I have discussed in this lecture the Hadamard transform. The Hadamard is a scientist. The name noted by the Hadamard transform. Hadamard. This is the basis function of this Hadamard transform. H2n. This is the representation of the Hadamard transform. Hn minus Hn. मतलब 1 minus 1 diagonal 1 minus 1, 1, 1. This
Here